Okay, so I promised you that I would show you what you could do with an Aryl diazonium ion. Aryl diazonium ion shown here. And what we can do with an Aryl diazonium ion is we can use copper salts to do what are called Sandmeyer reactions. So the Sandmeyer reaction, so if we use copper 1 bromide, we install a bromine. If we use copper 1 chloride, we install a chlorine. If we use copper 1 iodide, we install an iodine. So now you know how to install bromine, chlorine, and iodine in place of your Aryl diazonium salt. And then lastly, you can use copper 1 cyanide to install a nitrile. And you might remember that you can hydrolyze a nitrile using aqueous acid to produce a carboxylic acid. And so this gives us a new route to making a benzoic acid derivative. So let's say we're starting out with this compound here. This is isopropyl benzene. It's also known as cumene. So if we take cumene, we nitrate it in the first step, then we reduce it in these two steps of reduction followed by neutralization. Then we do the diazotization. We end up with our Aryl diazonium salt. We do our Sandmeyer reaction with our copper 1 cyanide, and then we can hydrolyze the nitrile to the carboxylic acid using aqueous acid and heat. Now, if you take your Aryl diazonium salt and you treat it with fluoroboric acid, so you see here this is HBF4, your Aryl diazonium gets converted into a fluorobenzene, and we call this reaction the Sheeman reaction, so useful to install a fluorine on an aromatic ring, which we haven't seen before in the class, so Sheeman reaction, very interesting. Also, if you take an Aryl diazonium and you heat it up in the presence of water, it just replaces the diazonium group for a hydroxyl group, so a new way to make a phenol derivative. If you take your diazonium and you treat it with hypophosphorus acid, so that's H3PO2 shown here, the diazonium salt gets replaced by a hydrogen atom. And this is useful when an amino group is needed on the ring temporarily to take advantage of its activating or directing effects. Now, this is a very specific example that he puts in the textbook. But let's say you wanted to make this very specific compound, 1,3,5-tribromo-benzene. Well, we saw earlier on that if you take aniline and you treat it with bromine, since the ring is so activated, it puts bromines in both ortho positions and the para position. And then you can do a diazotization followed by treatment with hypophosphorus acid. So in the first step, you're going to make the diazonium salt, right, shown here. But then with the H3PO2, the hypophosphorus acid, you're going to remove the diazonium salt. So kind of an interesting synthesis. Again, a very specific synthesis, but a good example of when it might be useful to replace a diazonium ion with a hydrogen atom. Aryl diazonium salts are also known to react with aromatic rings, and this process is called azocoupling. It's shown here, and it's believed to occur via an electrophilic aromatic substitution, like we would have seen in chapter 18. So you can see here's your Aryl diazonium ion. I mean, you can rationalize that this is a good electrophile. I mean, you have the positive charge right here. So we have an activating group here on this aromatic ring. So we have our nucleophilic attack, and then we end up producing our sigma complex or our rhenium ion. And then after a proton transfer here, we restore aromaticity, and we end up making our diazo compound. And diazo compounds have this extended conjugation, right? Double bond, single bond, double, single, double, single, double, single, double. Well, you get the idea here. It has conjugation all throughout, and therefore it exhibits color. And so what we can do is we can modify the starting materials by putting different substituents on the aromatic rings before we do our azo coupling, and that enables us to make a variety of different compounds that exhibit these unique colors. And these compounds are called azo dyes. And if you go back into chapter 18 in the textbook, they are discussed in a little bit of detail. Okay, question 22.26, propose an efficient synthesis for these transformations. So starting out with nitrobenzene, and we want to make 1,3-dibromobenzene. Well, a nitro group is a meta-director, and so if we treated the nitrobenzene with bromine and iron 3 bromide, that would install the bromine in this position, right? And then we could just do a diazotization after a reduction on the nitro, and then do Sandmeyer chemistry with copper 1 bromide. And that would replace the nitro group with another bromine. So let's outline what that would look like. So we're going to start off with our starting material, right? It's a good place to start. Anyhow, so we start off with our nitrobenzene, and we're going to treat that with some bromine and iron 3 bromide. And that's going to give us our meta-bromo nitrobenzene, so nitro, and then our bromine is going to be meta to it. Now we can reduce the nitro group down to an amine so that we can do our diazotization. So I'm going to use iron and aqueous acid for this. And then, of course, you have to wash it with sodium hydroxide to avoid having just an aniline ion. So now I've got my meta-bromo aniline. And now I can do my diazotization. And so you want to practice these so that you remember the conditions. And so it's going to be sodium nitrite, NO2, and HCl. That makes the diazonium ion. And then the Sandmeyer chemistry to install the bromine is copper 1 bromide. And so, you know what, I'm kind of running out of space here, so I'll just say, there's our product. Okay, 22.26c, we're trying to install a propyl group, and we also want to put in a hydroxyl group. Well, the only way we know how to install a hydroxyl group is to make a diazonium salt. So that means this is going to have to come from a nitro group, and remember that a nitro group is going to be a meta director. But also to make this propyl group, that's going to have to come from this carbonyl group, right? So that we avoid any kind of carbocation rearrangements. And also remember that a nitro group is strongly deactivating, and we can't do Friedel-Crafts chemistry, right? Because this has to be installed by Friedel-Crafts, and we can't do that if we have a nitro group installed. So that means we have to put this acyl group in first, then we'll do our nitration, then we can reduce both the carbonyl and the nitro down, diazotize, and then we can treat it with water and make our phenol. So it sounds like a lot, but it's not that bad. So let's get started here. So the first thing is our Friedel-Crafts chemistry. So we're going to use propionyl chloride and aluminum chloride, and that's going to install our acyl group. Here we go. So there we go. So we've got our ketone. So now we can do our nitration reaction. And to install our nitro, so we're going to use sulfuric acid and nitric acid. So sulfuric acid and nitric acid. All right, so now we've got our nitro group, and of course it's going to be in the meta position because the carbonyl is a meta director. So there we go, there's our nitro group. Now what's interesting about this is you can actually reduce both of these groups simultaneously just with a Clemmensen reduction. So if you do a Clemmensen, which uses the zinc mercury amalgam and HCl, it's going to reduce the nitro as well. If you want to do both steps individually, it doesn't matter. Either way is fine. So I'm just going to put here, I'll put step 1 is going to be my Clemmensen. So that's going to be my zinc mercury amalgam, HCl, and I'll cook that up. But of course, that's going to give me the aniline ion, right? NH3+, and I don't want that. So I've got to treat that with some sodium hydroxide after the fact, and that is going to give me my metapropyl aniline. Okay, so there's that. So now all I have to do is convert the amino group into a hydroxyl group. So first thing I'm going to do is diazotize. So I'll use my sodium nitrite and HCl. That's going to give me my diazonium ion. So N2, remember it's positively charged. It's a salt. 1, 2, 3. And then the last step is to install the hydroxyl. And for that, we just treat it with water and cook it up. And there we go. And in the last one, we were trying to convert benzene into para-tert-butyl benzoic acid. And the tert-butyl group, the only way we know how to install that is by Friedel-Crafts alkylation. And that's going to be a strong para director. I mean, it is an ortho para director, but it's going to strongly direct to the para position because it's so big. And so after we have that in, we could nitrate and then make a diazonium salt and then convert it into a nitrile and then hydrolyze to the carboxylic acid. So let's get started. Our first step is going to be the installation of the tert-butyl group. And so for that, we're going to need tert-butyl chloride and aluminum chloride. So that gives us tert-butyl benzene. So we'll draw that. Then we need to install our nitro group with our nitric and sulfuric acid. So we're going to put in our nitro group. Permit me to draw a circle in the middle of my aromatic ring just to make it a little bit easier for me. Anyhow, now we're going to reduce that down. So I'm just going to use iron to reduce it. And then we'll wash it with some sodium hydroxide. So that's going to give me the aniline. And so let's draw para-tert-butyl aniline. I guess I'll go back to drawing my aromatic ring correctly. So then we're going to diazotize and we're going to replace the diazonium with a nitrile. So in step 1, sodium nitrite and HCl. That makes our diazonium salt. Then Sandmeyer. Right, remember this is a Sandmeyer reaction. That's going to install our nitrile. So we've got our nitrile here. And we have our tert-butyl group out here. And the last step is just the hydrolysis, which is just aqueous acid and heat it on up.